Okay, hello. Welcome to the talk. I'm Stefan. I'm CTO of Match.io. And today we're going to talk about a typical problem in computer science and how we translate it, basically apply it for a profile of a developer that describes basically which kind of skills you have, what kind of jobs you're looking for. Because Match.io is an intelligent job matching platform actually for developers. And what we are trying to achieve, of course, helping developers filling out their profile and making recommendation in order to improve it. And today we talk first a little bit about theoretical computer science. It sounds boring, but hopefully you will, at the end, will learn something. Who of you still knows what a decision problem is? From theoretical, oh great, it's more than I thought, great. A decision problem in computer science is, for example, or in general, it's a question to a problem whether the answer is yes or no. Very, very simple ones are, for example, is a set sorted? The answer is yes or no. But there are also very interesting problems. For example, the so-called, it's really a German word, the Halteproblem. The Halteproblem is a decision problem that tells you whether a program, or declares actually whether a program halts or not. And this problem is not fully decidable. It's only semi-decidable. So basically, you only know when the problem halts, that it halts. If it does not halt, you don't know it actually. This is a very interesting problem. Another very famous problem in computer science is the Boolean satisfiability problem, the so-called ZAT problem. And the ZAT problems actually, it sounds very technical. We come a little bit to some technical concepts here because we apply it later on. And the thing is, it's heavily used in practice. Still, the complexity is very high. I come to some examples, but it's very helpful to solve really challenging problems. The question of this, basically the problem behind this problem is you have a Boolean formula, very simple one. You know it. Basically, you type in every day if you write an if clause or something. But the question is there an assignment to the variables of a Boolean function that satisfies basically the function or not? So does it yield to true or false? And if there is no such an assignment, then we need to prove that not such an assignment exists. We don't go about all the details, but the concept, in order to explain it, because it's very helpful to solve some interesting problems. It's very clear you have a clause is a disjunction of littlets, where a little bit is just a variable, a Boolean variable or its negation. And a CNF is basically a conjunction of those clauses. And we call those formulas satisfiable if, as I mentioned before, we find an assignment that finally evaluates to true. And if not, giving a proof, a proof that this formula is not satisfiable. And this proof tells me that really there's no such an assignment. That means, from a complexity point of view, I need exhaustively try all those different kind of combinations. So it sounds weird, but there are very, very interesting problems we can solve with that. But in general, maybe some of you know it still from computer science, theoretical computer science, doing study, the problem is NP-complete. It's still unknown whether there is an efficient algorithm for that. We come to a little bit later. And in order to really give you an idea how complex the problem actually is, if you have n variables and the search space is really n the power of 2 to n, so it's actually really exponential explosion here. Even for 1,000 variables, the search space is almost larger than the number of atoms in the universe. So it's really tough to solve. But we have tools for that in order to solve it efficiently. And still in practice, we can solve very, very interesting problems for a large number of instances. And we have tools, the so-called SAT solvers. So you give some such a formula, and at the end you get the results whether there is an assignment or not. And it's still actively researched how to improve those solvers since many, many years. If you're interested, try those links here. There are still competitions from also very famous companies, for example, AWS, Intel, Infineon, all those companies trying to help to improve those set servers because of some problems we're trying to solve. Some interesting fact here. Maybe some of you do know, NP-complete problem, or basically you still have the question whether for the set problem there is an efficient algorithm. And we believe, or many researchers believe, that there is no efficient algorithm, but there's no proof yet, since many, many years. It's a Millennium Prize on that problem, so if you can solve it, you get $1 million, just to let you know, if you have an idea. I think every day there's a solution, they think they proved it, but usually it turns out it's not a correct proof. And there's also a proof out that tells you how to not prove the problem. Or basically, it's very interesting. So basically, we can expect there's no efficient algorithm, probably not faster than exponential time. Also an interesting fact, because we couldn't still not solve it, is there are some polls out there, very interesting from researchers, to ask other researchers, do you believe that NP is unequal to P? So many of those believe, it's not a real proof, they believe. I think 90% believe that this equation does not hold. So, but still, it's just a fun fact. I was a little bit surprised there was a poll about that. Still no proof. And okay, what can we do with that? It sounds a bit very technical or very theoretical. What can we really do with that? It enables us, at least, find an assignment for very complex formulas. For some variables, when we do it usually in our if clause or something, it's very trivial. For 2 or 4 variables, that sounds very easy. But they're very interesting applications. For example, for hardware problems. In hardware, we are trying to really prove that the digital model of such a hardware, or basically function, is always correct. For example, suppose you have a CPU, and there's an addition in it. Of course, there's a physical realization, and you would like to prove that this addition, or basically the arithmetic logic unit, is always correct. Of course, you want to have correct additions. And this is where form verification that actually uses set solvers is trying to really give you a proof that your design is correct, 100% correct. That's not something we talk about unit tests. The unit test is not always correct. And of course, if you have 100% coverage in terms of data, of course, you get a proof. But that's often not the case. And in software, also very interesting, you would like to prove some liveness properties. For example, if you fly with an airplane, and typically in those airplanes, you have so-called traffic collision avoidance system. And it's very small kind of code in C, very ugly code, honestly. But there's a software proof that this kind of small program delivers always a correct answer that the airplane's not going to crash. So really a proof. And in such a scenario, you're very interested in a proof. Another example is AWS, since years, trying to formally verify that your security settings are correct in any kind of scenarios. So you get a proof for that. Very, very cool. So you get 100% confident that your settings is going to be right. Because the underlying problem formulation, or basically those set solvers, exhaustively trying out all those combinations. How does it work in practice? We had there was a talk, I think, at 2 or something. It was about, forget about it, AI or something doing mathematical modeling. I forgot the exact name, sorry for that. But it turns out we still have very, very powerful tools to solve problems. Not just throw away, okay, we apply some machine learning technique or AI technique in model. In general, we have solutions for that. And this is, for example, an example for solving practical problems with already available solutions. And this is a very typical approach to solve decision problems and translate it to a satisfiability problem. You take your problem domain, you convert it into the CNF we talked about. It's basically a huge Boolean formula with thousands of variables, thousands of clauses, and you give it to a set solver, and the set solver gives you an answer whether there's an assignment or proves that there is no such an assignment. The basic question is, for example, you have two implementations of the software, for example, a very prototype implementation, or for example, you have an original implementation, legacy one, and you would like to compare to a new implementation. You would really compare whether both programs always leads to the same result. So we get a proof then, finally. And of course, you get an answer, true or false, or unknown. Unknown means it took too long to compute a solution. Honestly, solving that problem takes some time. It depends, of course, the problem instance. It can take a minute, seconds, or up to hours or days. But in many cases, it's worth to do it when you finally get a proof that something is really correct. Taking the result, you map it back to your problem domain. So the real task is taking a Boolean formula, translate it into a CNF, using an asset solver, and I get a result. Okay, what the hell is something with a job? Okay, it sounds very technical and very theoretical here. In match.io, we're trying to compute matches. And the basic idea, basically the input what we have is a developer profile so basically we call a candidate. It fills out, for example, what's your skill level, what is your desired salary, are you open for remote work or hybrid work, and things like this. And then we take the job profile and compare them basically, and trying to match those together and give it to developers and to the jobs. And this is somehow how it looks like at the end. So you can then finally accept the match or not. So from the more modeling point of view, you have jobs. You have a lot of jobs and a single developer profile, and the question is basically, do they match? And sometimes they match. For example, with this job, with that job, this is then finally a match. You can accept it and things like that. Very easy to understand. Or to match with a different job. Or what happens if basically the profile does not match with any of the jobs? That's something probably wrong with your profile. Or there's simply no job available. And at Match.io, we're trying to help actually developers at the end to improve their profile. And I want to give you an example, basically how we help developers to improve their profile. And the thing is, let's talk about an example. The question, we translate it now to a decision problem. And the decision problem is there a certain number of matches I can get under a certain salary? And the application at the end is, I would like to maximize the salary. It doesn't necessarily mean that all of us would like to boost our salary. Of course we want, but it also turns out that, I will show you at the end, that the salary is also decreased in order to get some matches. But at the end, it's an optimization problem that tells me, or is formulated as an optimization problem, I would like to optimize the salary that at least I get 10 matches in this formulation. Oh, you have a candidate, and you replace basically the salary and the match. You build a big OR formula, and you sum up basically all the number of matches, and it should be at least 10. And this can be translated into the Boolean satisfiability problem. You start basically with a certain salary and doing a binary search. You take your current salary and compute, is there any match under this current scenario? If not, you just say, okay, cut it by half or something, and ask again. And compute again a decision problem. Is there no at least 10 matches with that kind of setup? And you do it actually until you get an optimum value. So you regularly compute or solve a decision problem. And the nice property is that those formulas, it's very actually known from research that those numbers or those formulas can be translated into CNF with it can be at least translated efficiently. That means I get a linear or polynomial-sized formula, so the problem does not even more explode. So, but still, the underlying problem is still an exponential problem. What we get at the end, we took some benchmark of match.io. We took a certain subset of candidates with the range of between 30K and 152K salary range, and for all those, we're trying to optimize the salary. For some candidates, what we can see here is that we double the salary. You can imagine you fill out your profile, you start with some salary, even for junior developers maybe, or from not yet experienced developers that just start with some very low salary. Based on the job market, we know we improve basically automatically the salary to 200%. And for some candidates, we reduce the salary to 90% because it was basically too low based on the market data we have. Market data, again, is the job profiles we have. And in mean, we have something like 111%. So basically, most of them get increased of the salary. So not increased, basically, the number basically is above the salary they currently have. At the end, 47% got an upgrade, and 43% got a downgrade. So basically what we at the end did is that we aligned all the profiles or basically we cut the extreme. Of course, there are some developers that have really high paying, basically want really high paying jobs, but we proposed, in order to get at least matches, to reduce the salary. So usually when we take, when we have a look at these numbers for matches, some of those developers, basically the maximum of the new matches went to 97%, at least 10 matches, of course. That was our requirement from the problem formulation here, right? We told the decision problem to at least 10 matches. Of course, we can try to optimize here, but it was a minimum requirement. So that means I get at least 10 matches. And I mean, we have 21% more matches. So we took basically a very typical problem in computer science, very old one, and we have very efficient solutions for that. Efficient solution in practice, in theory, in general, it's still a hard problem, but the problem instances getting solved very efficiently. Of course, we still have exponential search space, and we need to go through it in order to get a proof or get a solution. But we're able to use such simple tools, actually, still available, employed in very fields, to solve that kind of problem. What I wanted to say is, we could still try to take our current problems we have and take those available tools we have and solve those kind of problems. Thank you very much.